what are the things are related to train resistance and tractive power. This is the chapter number 25 in your Agarwal book. I am directly referring this book because in this book very well they have the author have has described or the authors they have described about the train resistance and also the numerical which is involved with this train resistance. So also you can follow this book, but I am just dictating, and also it will I'm giving you the points which will be picked up from this chapter. This is important. So suppose if we see first introduction, various forces offer resistance to the movement of the train on the track. These resistances may be the result of movement of the various parts of the locomotives like engines, as well as the friction between them, the irregularities in the track profile, or the atmospheric resistance to a train moving at a great speed. So resistance may generate from the various parts of the railway. Train rail is part of us, civil engineering part, and the train is the mechanical part. Mechanical engineer, they normally handled this mechanical part or train part, and these resistance will come from the various parts of the locomotives or wagons, as well as the friction between them and the irregularities in the track profile or the atmospheric resistance. Atmospheric means wind pressure, mainly the main cause of atmospheric resistance to a train moving a great speed. The tractive power of a locomotive should be adequate enough to overcome these resistances and haul the train at a specified speed. So haul means the pulling. The pulling of the locomotive is important to us, because if the engine can't pull out the train properly, then this is not our intention or our aim to complete the operation, because our intention is, as a civil engineer, how a locomotive or the complete train or the bogies will go smoothly through the track. This is our part as a civil engineer. Okay, we cannot we don't see any kind of the problems related to engine mechanical problem. Just we are concerned about the problems which are related to the track. Okay, any track resistance, any kind of the movement of the various parts which are directly can generate the resistance during hauling or pulling the train by the locomotive, as well as the resistance may generate from the bogies also. So normally as a civil engineer also our intention is how can we solve, or how can we overcome this type of resistance, or what are the actual resistance which we will face or which are normally generated, and we have to deal with this resistance. Achha, number one, you can see in this PDF file the resistance due to friction. Okay, resistance due to friction. Resistance due to friction. Resistance due to friction is the resistance offered by the friction between the internal parts of locomotives and wagons. Resistance due to friction is the resistance offered by the friction between the internal parts of locomotives and wagons, as well as between the metal surface of the rail and wheel to a train moving at a constant speed. So these are the theory. Actually you can read from the book. This is the just theory. Theory in this chapter. Theory is important, but numerical is more important than theory. This resistance chapter. So one is resistance due to friction. Where the friction can generate. Friction can generate from the railway track, and friction between the wheel and the track. This is the one of the part where friction can generate. General friction is there. This is depend on the type of bearing, lubricant used, the temperature and condition of the bearing. Internal resistance, the resistance is consequential to the movement of the various parts of the locomotive and wagons. rolling resistance. This occurs due to rail wheel interaction on account of the movement of steel wheels on a steel rail. This is one of the important, just the name, rolling resistance. Okay, rolling resistance can be defined as R1 as a formula. R1 equals to 0.0016 W. Okay, this formula is important because this formula is needed to us during solving numerical under resistance. When we are concerned about resistance, this is the first resistance which will come during calculation, that is rolling resistance. Rolling resistance is defined as R1. R1 equals to 0.0016 W. Okay, you can note down. If you have pen and paper, you can note down this R1 equals to 0.0016 W, because this formula is needed for calculation of numerical, where R1 is the frictional resistance independent of speed and W is the weight of the train in tons. Okay, W is the weight of the train in tons. Number 2, resistance due to wave action. Okay, what is wave action? These things are important to know, and the formula. When a train moves with speed, a certain resistance develops due to the wave action in the rail. Similarly, track irregularities such as longitudinal unevenness and differences in cross levels also offer resistance to a moving train. Such resistances are different for different speeds. There is no method for the precise calculation of this resistance, but the following formula has been evolved based on experience. So when a train moves with speed, a certain resistance develops due to the wave action in the rail. Similarly, track irregularities. Normally, this wave action is directly involved to the irregularities of the tracks. Very nominal irregularities of the track can be seen. However, some irregularities we cannot omit, we cannot remove. So due to these irregularities, some resistance are generated, and it is called the wave action. Okay, and we can calculate this resistance, or we can define as R2, and R2 equals to 0.0008 WV. Okay, W is the weight of the train in tons, V is the speed of the train in kilometer per hour. So first is resistance due to friction, second is resistance due to wave action. Okay, R1, R2. Third is resistance due to wind. You can note down this R2 formula. R2 equals to 0.4008 WV or 0.0008 WV. Resistance due to wind. Third number resistance. When a vehicle moves with speed, a certain resistance develops as the vehicle has to move forward against the wind. Wind resistance consists of side resistance, head resistance, and tail resistance. The important thing is you should not keep in your mind that what is the wind resistance, what is the wave action, what is the friction. Just if you have any question regarding what is the friction, you can read out, but important is this formula actually and this name. Friction due to resistance due to friction, resistance due to wave action, resistance due to wind. These things are important. So when a vehicle moves with speed, a certain resistance develops. A vehicle has to move forward against the wind. Wind resistance consists of side resistance, head resistance, and tail resistance. But exact magnitude depends upon the size, shape of the vehicle, its speed and wind direction, as well as its velocity. Wind resistance depends upon exposed area of the vehicle and the velocity and direction of the wind. Okay. Normally, as we know, suppose I'm describing, V is the velocity of wind at angle theta. When any angle is there, we can convert into if we need in the x direction, then we convert it to V cos theta. If this angle is known to us and the magnitude of the value of the velocity is known to us, we can convert in the direction of x, the V cos theta. if we need in the direction of y, we can convert it v sin theta. So this v and angle of theta is it should be known to us, then we can convert into x direction or in the y direction. Acha. So v is the velocity of wind at angle theta. The horizontal component of wind v cos theta, horizontal component this x direction, v cos theta oppose the movement of the train. Wind normally exerts maximum pressure when it acts an angle of 60 degree. This is one of the maybe the MCQ question. When wind exerts maximum pressure, okay, when wind exerts maximum pressure, it may be a MCQ question. So wind normally exerts maximum pressure when it acts an angle of 60 degree to the direction of movement of the train. Okay, so wind resistance can be obtained by following formula. So same like R1, R2, wind resistance are defined by R3, and the formula of R3 is 0.00017 A into V square, where A is the exposed area of vehicle and V is the velocity of wind. Okay, don't be confused because this velocity is the velocity of wind, but during calculation it is very difficult to remind that which V is this. Okay, and A also we don't know the exposed area where the wind is interacting with the vehicle, how much area with how much area the air is interacting with the vehicle. This is very difficult to find out. So that's why the some simplification are there. Just see here. Studies also support the fact the important factors that affect wind resistance are the exposed area of the vehicle and the relative velocity of the wind, vice versa that of the vehicle. In fact, wind resistance depends upon the square of the velocity of the wind. The following formula has been empirically established on the basis of studies. Okay, suppose this is the direction of the train in this figure, this resistance due to wind in this figure. If this is the direction of train movement and this is the direction and velocity of wind. Okay, and obviously if problem is given to us, then in problem it should be mentioned the angle of the or the direction of the wind. Okay, which is defined by or denoted by theta. This theta value should be given in the our problem, in numerical problem. So when this theta value is available and the velocity of the wind is available, we can calculate the resistance due to wind. Okay, and already I have said that the if this theta is available to us, also we can convert in the x direction or in the y direction, easily we can convert. Now the formula which is actually needed in our numerical problem, because this formula is difficult to adjust in our numerical problem or to calculate the resistance due to wind. So there is one formula, that is R3 equals to 0.0000006 not 0. Okay, 6 W V square, where R3 is the wind resistance in tons, V is the velocity of train in kilometer per hour. So I have said that this V is very difficult for us because during calculation it is not possible always to remind that this V is for wind velocity. So that's why one simple formula is there, this W 0.000006 W V square, where this V is velocity of the train in kilometer per hour and W is the weight of the train in tons. So easily we can calculate the R3 because this velocity is universal for any train resistance problem, because V is all over the same which is the velocity of the train, and W is the same weight of the train in tons. So then we can easily calculate the R3 value. Next is resistance due to gradient. So up to that, very important, because resistance due to friction, resistance due to wave action, and resistance due to wind, because this is general resistance which are normally generated for any kind of track, any kind of railway track. Normally this kind of resistance are generated: friction, wave action, and wind. And from these three, R1, R2, R3, we can calculate the speed, actual speed of the train, actual speed of the locomotive. Okay, and after that, after R1, R2, R3, from this resistance due to gradient, or R4, now these resistances are normally generated due to gradient. But that means if gradient is present in the track, then only this resistance can be generated. But if your train or your locomotive is passing through a normal rail line or normal track, railway track, then only these three resistance will be generated: friction, wave action, and wind, resistance due to wind. Okay, now resistance due to gradient. When a train moves on a rising gradient, it requires extra effort in order to move against gravity, as shown in figure. Okay, assuming that a wheel of weight W is moving on a rising gradient, OA, the following forces act on the wheel. This is the one gradient has drawn, and this the OA line. Through OA line, the wheel is moving and wheel is rising. Assuming that the wheel of weight W is moving on a rising gradient OA, the following forces act on the wheel: weight of the wheel, which acts downward; normal pressure N on the rail, which acts perpendicular to OA; resistance due to rising gradient, that is R4, which acts parallel to OA. This parallel to OA, R4 is normally considered. This derivation or this type will not come, but for understanding we will go through it. R4 is which acts parallel to OA. These three forces meet at a common point Q. This is the Q point, middle of the or center point of the wheel. Okay, then, and the triangle QCD can be taken as triangle of forces. This QCD, triangle of forces, taken as the triangle of force. It can also be geometrically proved that the two triangles QCD and AOB are similar. QCD and AOB are similar. From triangle QCD, R4 equals to W sin theta. R4, this is W, W is the weight of the wheel, and when we are converting in this direction, so R4 equals to W sin theta. Okay, from OAB, then R4 equals to W into AB. AB is the hypotenuse by OA. Okay, AB by OA. This is the sin theta. In actual practice, the gradients are very small, and therefore O is approximately equal to OB. This OA equals to OB, because this gradient is very small. This theta value is very small. That's why R4 W equals to AB by OB equals to W into percentage slope by 100. This is the actual formula of R4, or resistance due to gradient, W into percentage slope by 100. This means that if the weight of the train is 50 tons and the slope is 1 in 50 or 2%, the resistance due to gradient is R4 equals to W into percentage slope by 100. W is 50 in tons into 2. 1 in 2 means 1% means 1 in 50. So normally we can calculate the resistance of the train. due to gradient. It may be noted that here that when a train is ascends a slope, extra effort is required to overcome the resistance offered by the gradient. The position is, however, received when the train descends a slope, and the resistance offered by the gradient helps in movement of the train. Whatever, the rising gradient is important, but falling gradient is not said anywhere. But rising gradient is important because extra force or resistance is generated in rising gradient. Resistance due to curvature. When the train up to R4, okay, R4, R1, R2, R3 is are in normal condition. R4 only when gradient is introduced in the track. After R4, resistance due to curvature. Curvature also, when curve is in the track, then the curvature or resistance due to curvature will be considered. When a train negotiates a horizontal curve, extra effort is required to overcome the resistance offered by the curvature of the track. Okay, curve resistance is caused basically because of the following reasons. The vehicle cannot adapt itself to curved track because of its rigid wheelbase. This is why the frame take up the tangential positions as the vehicle tries to move in a longitudinal direction along the curve as shown figure. On account of this, the flange of the outer wheel of the leading axle rubs against the inner face of the outer rail, giving rise to resistance to the movement of the train. Curve resistance can sometimes be the result of longitudinal slip, which causes the forward motion of the wheels on a curved track. The outer wheel flange of the trailing axle remains clear and tends to derail. The position worsens further if the wheelbase is long and the curve is sharp. Curve resistance is caused when transverse slip occurs, which increases the friction between the wheel flanges and the rails. So basically, there is a friction. Cause of resistance due to curvature is the friction, maybe longitudinal friction. Okay, longitudinal friction, which is normally generated from the outer wheel of the leading axle. Okay, flange of the outer wheel. One cause is flange of the friction between the flange and the railway track. Another is this is one reason. Another reason is the horizontal movement, that is called slip. Normally, horizontal movement of the wheel, very little or very less friction is there, but however due to this friction the resistance can be generated, and we should consider that kind of resistance which are normally generated due to curvature. Poor track maintenance, particularly bad alignment, worn out rails, improper levels also increase resistance. Inadequate super elevation increases the pressure on the outer rail, and similarly excess super elevation puts greater pressure on the inner rails. These theories are just for understanding. Okay, this is will not come as per my best knowledge. These theories are normally not asked in the exams, but numerical question may asked. Okay, numerical questions are important from this chapter. Same figure is given, various reasons, and which are tried to given for understanding the resistance due to curvature. The value of curve resistance can be determined by the following equation. Curve resistance equals to C into Fg by R, where F is the force, sliding friction, G is the gauge of the track, R is the mean radius of curve, and C is the constant, which depends on various factors. And the equation indicates that curve resistance is increased with increase in gauge width, and the resistance is inversely proportional to the radius, that is increases with an increase in the degree of curve. But finally, which is required to us, that is empirical formula, or that is R5. Already we have idea R1, R2, R3, R4, and now the R5. R5 is the 0.0004 WD, where W is the weight of the train in tons and D is the degree of curve. But the problem is R5 is different for different gauge. For broad gauge, this value is 0.004. For meter gauge, this value is 0.0003. For narrow gauge, this value is 0.0002. Okay, so for different gauges, these values are different. Also, if it means that the 4-degree curve on a broad gauge line, the curve resistance for a chain weighing 250 tons would be 0.004 into 250 into 4, 0.4 tons. There is a compensated gradient for curvature. Compensations are also provision of compensation also given, but you can read out from the book. This is will not cover in our numerical problem. Special characteristics of curve resistance. This is not important. Now the resistance due to starting and acceleration. Okay, R6. Trains face this resistance at stations when they start, accelerate and deaccelerate. The values of these resistances are follows. Resistance on starting R6. R6 is 0.15 W1 plus 0.005 W2. Resistance due to acceleration, that is R7. Okay, where W1 is the weight of the locomotive in tons, W2 is the weight of the trailing vehicles in tons, W is the total weight of the locomotive and vehicle in tons, that is W1 plus W2. So W1 is the weight of the locomotive in tons, W2 is the weight of the trailing vehicles in tons, and this W is the total weight of the locomotive and vehicle in tons. ठीक है, that is W1 plus W2, and A, small a, is the acceleration which can be calculated by finding the increase in velocity per unit time, that is V2 minus V1 by T, where V2 is the final velocity, V1 is the initial velocity and T is the time taken. This is the important table where you can find all the formulas. Resistance due to friction formula is 0.0016 W. Resistance due to wave action, the formula is 0.00008 WV. Resistance due to wind, the formula is 0.000006 WV square. Resistance due to gradient, R4, the formula is W into percentage of slope by 100. Curve resistance, formula is 0.0004 WD. Resistance due to starting, 0.15 W1 plus 0.005 W2. Resistance due to acceleration, 0.028 small a into W. These formulas are required to find out the resistance. However, already I have said that this is R1, R2 and R3 is in normal condition, where no gradient is there, no curve is there, no starting, no acceleration, okay, or no deacceleration, such type of incidents are there. Then only this R1, R2, R3 are important, and from this R1, R2, R3 we can calculate the speed of the vehicle in general condition. In normal condition we can find out the speed of the train or locomotive. But after that, when the gradient, curve, starting, acceleration, such type of incidents are included in the our problem, then we should consider then R4, R5, R6, R7. We can see in the numerical. However, let's see what are the other things which are involved in this this type of problem. Tractive effort of a locomotive. Okay, the tractive effort of a locomotive is the force that the locomotive can generate for hauling the load, hauling, that is pulling, the tractive effort of a locomotive should be enough for it to haul a train at the maximum permissible speed. There are various tractive effort curves available for different locomotives for different speeds, which enable the computation of the value of tractive effort. Tractive effort is generally equal to or a little greater than the hauling capacity of the locomotive. If the tractive effort is much greater than what is required to haul the train, the wheels of the locomotive may slip. Okay. A rough assessment of the tractive effort of different types of locomotives is provided in the following section. So, tractive effort is normally nothing but it is actually pulling capacity of the train. Okay, this thing is not a big thing, very simple. Steam locomotive, for steam locomotive this value is can be calculated from this formula. For diesel locomotive, I am going to start from this diesel locomotive because this steam locomotive is not available now these days. So I will start from the diesel locomotive. So for diesel locomotive, tractive effort of a diesel electric locomotive can be based by the following empirical formula. This is T. T means tractive effort of locomotive. So T equals to 308 into RHP by V. Okay, T is the tractive effort of a diesel electric locomotive. RHP is the rated horsepower. Already you have idea what is horsepower in physics. Already we have seen, we have studied what is horsepower. So this is the rated horsepower of train or engine, and V is the velocity in kilometer per hour. Okay, this is for diesel locomotive. For electric locomotive, the tractive effort of an electric locomotive varies inversely with the power of speed. The empirical formula for calculating the approximate value of tractive effort for an DC electric locomotive, T equals to A by V cube. For an AC electric locomotive, T equals to A by V5, V to the power 5. Okay, so where A is the constant depending upon the various characteristics of the locomotive. The important characteristics of the three types of tractions are normally the important characteristics of three types of tractions are compared in table, but this table is not important. The hauling power of a locomotive depends on the weight exerted the driving wheels and the friction between the driving wheels and the rail. The coefficient of friction depends upon speed of the locomotive and the condition of the rail surface. The higher speed and the locomotive, the lower will be the coefficient of friction, which is about 0.1 for high speed and 0.2 for low speed. The condition of the rail surface, whether wet or dry, smooth or rough, etc., also plays an important role in deciding the value of the coefficient of friction. If the surface is very smooth, the coefficient of friction will be very low. So basically these theories behind the hauling power you can read, but it is not important for exams. But what is hauling power? Hauling power is the number of pairs of driving wheels as a formula into weight of exerted on each driving axle into coefficient of friction. Thus, for a locomotive with 3 pairs of driving wheels, an axle load of 20 tons and a coefficient of friction equal to 0.2, the hauling power will be equal to 3 into 20 into 0.2. So, number of pairs of driving wheels, this is important. This number is important. Weight exerted on each driving axle, this is important. Number, weight and coefficient of friction. Number, weight, coefficient of friction. Coefficient of friction already mentioned, that is 0, which is about 0.1 for high speed trains and 0.2 for low speeds. So the coefficient of friction we can put 0.2 or 0.1. If you put 0.2 for every cases, no problem. Almost you will get the similar result if you put 0.1 or 0.2. Weight exerted on each driving axle will be mentioned in the numerical question. Number of pairs of driving wheels also will be mentioned in your numerical. Now the problem is there. Okay, and this is the important to us. Actually, this problem is important to us. How can we solve this problem? How can we calculate this problem? This is important to us. The first problem, okay, and this is also assignment. We have 3 problems. Okay, these 3 problems are assignment for you, because these are very important problems, numerical problems for your this resistance chapter. Now see, let's see the first problem. It is said that calculate the maximum permissible load that a broad gauge locomotive with 3 pairs of driving wheels bearing an axle load of 22 tons each can pull on a straight level track at a speed of 80 km per hour. Okay. Also calculate the reduction in speed if the train has to run on a rising gradient of 1 in 200. What would be the further reduction in speed if the train has to negotiate a 4-degree curve on the rising gradient? Assume the coefficient of friction to be 0.3. Already coefficient of friction is given. So let's see the solution. Acha. First, in the question, it is mentioned that or it is asked that calculate the maximum permissible load that a broad gauge locomotive with 3 pairs of driving wheels bearing an axle load of 22 tons each can pull on a straight level track at a speed of 80 km per hour. So when it is mentioned that straight level track, so when it is mentioned that straight level, that means no gradient is there, no curvature is there, okay, and no other resistance or the other condition of resistance which are normally generated due to suppose for your accelerating or your starting condition. So such type of resistance are not involved in straight level track. That's why in solution number A, suppose hauling power of the locomotive, this formula is used. Hauling power of the locomotive equals to number of pairs of driving wheels into weight exerted on each pair into coefficient of friction. Just this formula, just we have seen last. Hauling power. Hauling power is equals to number of pairs of driving wheels into weight exerted on each driving axle into coefficient of friction. This formula is needed first. So as per mentioned value in the question, so number of pairs of driving wheels is 3, already mentioned 3 pairs. This 3 of driving wheels bearing at axle level of 22 tons, already mentioned 22. Then the assume the coefficient of friction is 0.2, so into 0.2. So this is the value. This is the hauling power. This power is required to haul the train 13.2 tons. Okay. Now this value is available to us. This is very important to us because this is required to calculate other values. Next, the total resistance negotiated by the train on a straight level track at a speed of 80 km per hour. The formula is R, total resistance. R equals to resistance due to friction. Okay, this is normal. Resistance due to wave action. This is also normal condition. And track irregularities plus resistance due to wind. Already I have said these are the very normal resistance which are generated in the track or in normal conditions. Resistance due to friction is formula is 0.0016 W. Resistance due to wave action and track irregularities formula is 0.0008 WV plus resistance due to wind formula is 0.000006 WV square. Now substituting the value of V is the velocity of vehicle 80 km per hour. Now put this V in these places, okay, and finally you will get this value, R equals to 0.01184 W, where W is the weight of the vehicle. Assuming the total resistance equals to hauling power. this hauling power, we can assume this hauling power is equals to this total resistance. Okay, this total resistance, this R value. So if the R this hauling power is 13.2, so 0.01184 W can be written as equals to 13.2 tons. Normally we can calculate the W value, weight of the vehicle. Weight of the vehicle is 1114.86 tons. Okay, approximate 115 tons. So now weight of the vehicle is available. Next in the question it is asked that also calculate the reduction in speed if the train has to run on a rising gradient of 1 in 200. Okay, if gradient is present in the track and the gradient is 1 in 200. 1 in 200 means 1 by 200. 1 by 200 is 0.005. Okay, percent. 1 in 200 means 1 by 200 is 0.005%. Now on gradient of 1 in 200 there will be an additional resistance due to gradient is equal to W into percentage of slope. Since hauling power equals to total resistance 13.2, again this formula 0.0016 W plus 0.0008 WV plus 0.000006 WV square plus now gradient is introduced, so formula of gradient will be added with this formula, that is W into 0.5 by 100. Okay, or simply we can write 0.005 W into 0.005. okay, because already you have seen if gradient is there the formula is W into percentage of slope. Okay, so that's why we in this solution it is added with the actual formula. The extra thing is this resistance due to gradient part is added 0.005. so again calculate the W value. Okay, after calculate the V. Now V is important because already we have the W value. Now V is important because velocity is reducing due to gradient, so V is now important. Already there are number of resistance are there, but additionally when the resistance due to gradient is introducing, then what would be the velocity of the vehicle is important. So when W value is available, now from this equation we can calculate the V value. Already the V value is 80 km per hour, but due to gradient now the V value is 48.13 km per hour. So easily we can calculate the reduction in speed, that is 80 minus 48.13, and the reduction in speed is 31.87 km per hour or approx 32 km per hour. This is the second question. Also calculate the reduction speed if the train has to run on a rising gradient of 1 in 200. Next, what would be the further reduction in speed if the train has to negotiate a 4-degree curve on the rising gradient? Now another thing is added, that is curvature. Let's see, on a curve of 4 degree on a rising gradient of 1 in 200, curve resistance will be equal to R equals to 0.004. This formula is already we have seen, resistance due to curvature 0.0004 into degree of curve into WT. So 0.004 into 4 into W, that is after this multiplication 0.0016 W, and hauling power of locomotive that is total resistance. Now all the resistance will be added. The hauling power is 13.2. This is resistance due to friction. This is wait. This is resistance due to wave. This is resistance due to wind. This is resistance due to gradient, and finally this is resistance due to your curve. Okay, curvature. By substituting the values of W, again the W value is known to us, 114.8 tons in equation, and solving further, V equals to, after introducing the curvature, the V value is 43.68 km per hour. Therefore, further reduction in speed is already introducing the gradient in the track. The speed become 48.3 from 80 km per hour. Now the speed, after introducing the curvature in the track, the speed become 43.68 km per hour. So reduction is speed is 48.13 minus 43.68 is 4.45 km per hour. And maximum permissible train load already calculated, 114.86, approximate 115 tons. Reduction in speed due to rising gradient calculated 31.87 km per hour. This is, and further reduction in speed due to curvature calculated 4.45 km per hour. So this type of numerical can be asked in your even semester exam also. You can face such type of numerical, and this is also important for your any engineering service exams, any where the broad questions are asked in any exams where the broad questions can be asked. You can face such type of problem. So as a assignment, you should solve. Already I have dictated this numerical. Second, this one, 25.2, 25.2, 25.3 and 25.4. These three problems you should solve by yourself. Okay, and you should send to me in my mail. These are important, and if you solve then you can understand properly. Okay, just wait, I am taking attendance. Another thing is I am not going to provide you any PPT for this for today's class, because already all the things are mentioned in your this book, Agarwal book, ebook. This ebook is available to you. Already you have this book, so you can study this from this chapter. Everything is mentioned in this chapter, and very simply they have mentioned. So you can follow this chapter for track resistance or hauling resistance, whatever is provided. Also this is not mentioned in your syllabus, also your conventional syllabus, but important in your semester exam also. This type of question may asked, or this type of numerical may asked to solve. So I am not going to give you any PPT. So thank you. Already I have taken attendance. You can leave. Thank you. Mm-hmm. Mm-hmm.